So in this lecture, I'm going to discuss about statistical process control. Statistical process control is a quantitative approach based on a measurement of process control. Scientists believe that in the use of statistical process control chart, a key method for identifying special and common causes and assisting diagnosis for quality problems. This aim was to remove the quality problems related to special causes of failure. This was achieved through training, improved machinery, and equipments, so on. So this SPC is a very quantitative approach, not qualitative. So quantitative means you're going to give some values how this process is performing. Okay, so you're going to measure the process control using this kind of statistical process control technique. So SPC enables the production process to be brought under control. So main purpose of SPC is to make sure that it is under control. Okay. The remaining quality problems was considered to be related to common causes, that is, they were inherent in the design of production process. Eradication of special causes enabled a shift in focus to common causes to further improve quality. They also states that statistical quality control chart compares process performance data to computed statistical control limits drawn as limit lines on the chart. So we are going to just draw a graph. From the graph, we are going to analyze whether the process is under control, and we are going to set the control limits here. Okay, control limits, like example, there will be upper control limit and lower control limit, and there will be a mean average limit. So where the process is whether it is happening under the control or it's going out of control, that's we can able to measure using this kind of statistical control chart. So control charts. The use of control chart focuses on the prevention of defects rather than their detection and rejections. In business, government, and industries, economy and efficiency are always best served by prevention. We are going to prevent the defects rather than making it happen in the making it happen, and then we are not going to remodify it. We're just going to prevent the defect, okay, on happening. So it costs much more to produce an unsatisfactory product or service than it does to produce a satisfactory one. There are many costs associated with producing unsatisfactory goods and services. These costs are in labor, materials, facilities, and the loss of customers. The cost of producing proper product can be reduced insignificantly by application of statistical process control charts. There are two categories of control charts based on the type of data collected. One is variable control chart and the one is attributes control chart. So in this graph, I'm just going to summarize what is variable control chart and attribute control chart. In the control chart, you can see there are two categories, attribute and variable control chart. See, the variable means it is used with continuous or measured data. So whenever we're using continuous data, whenever the processes are continuously getting some values or measuring some values regularly, okay, that kind of data can be measured in variable control chart. And the second point is raw data can be logically fractional when measuring. Okay, be logically fractional. Okay, in attribute you can see is used with discrete data. Discrete data means you can say take only the set of data and check whether it is good or bad. Okay, not the continuous set of data. We're not going to take that. We're going to take some discrete data, one or two data, and going to check whether it is correct or not, or whether it is control or not. Okay, raw data can only be in whole numbers when counting. So in variable control chart, we're going to individual and moving range chart, X bar R chart will be used here. And in attribute, we can say there are two types, that is C and U chart and N and NP chart. So NP and C and U chart. There are four types of chart comes under attribute control charts. So P chart is to for tracking the fraction of units defective, where the sample size is not constant. Okay. So it is used to study the proportion of non-conformance or defects. How much percentage or how much units are not are defective in terms of percentage. NP means you used to chart the number of defective units in sample size is constant. So P means sample size is not constant. NP means sample size is constant. Similarly for the C and U are used to chart the number of defects in the constant sample size. And when U chart goes for when the sample size is changing. When the sample size is not, I mean, continuously changing, then we can go for U chart. Okay. And this is a basic comparison of different control chart. And you can see here statistical measure plotter. So parameters are given here. And in terms of X bar R chart, P chart, and C chart, are given like type of data required, like variable data. Here in the P and C chart, we can say attribute data because it's coming under attribute. Okay. Field of application, control of individual characteristics, control of overall fraction of defective of process, and advantages provides maximum utilization of information available from data, provides detailed information, process average, and variation for control of individual dimensions. So individual product unit or the performance can be improved with help of it's an R chart. Whereas in the P chart, you can say data required are often already from the inspection records. So here in the P chart, already the defect has been happened, and that data you're going to get from the team, and you're going to do the analysis. Okay, easily understood by all person provides overall picture of quality. So some advantages as P chart, but provides a measure of defectiveness for C. Okay. So disadvantages cannot be used with the go and not go type of data, and not understood unless the training is provided. In the P chart, it does not provide detailed information for the control of individual characteristics. Does not recognize different degrees of effectiveness in the units of product. Does not provide detailed information for control of individual characteristics. So sample size usually 4 or 5. P chart usually the 50 or 100 depending upon the type of data you get. Okay, so this is the basic comparison of different control charts that we are going to analyze in our statistical process control chart. So control chart and the normal distribution. The construction, use and interpretation of control chart is based on normal statistical distribution. The center line of the control chart represents the average or mean of the data. Is X bar. Okay. And that is another two important limit like upper control and lower control limits, which represents the mean plus and minus 3 standard deviation of the data. That is x plus 3s. Either the lower case means you're going to put minus symbol. If the upper limit means you're going to put the plus symbol. The normal distribution and its relationship to control chart is represented on the figure. Normal distribution is described entirely by its mean and its standard deviation. So the normal distribution is a kind of a bell-shaped curve that is symmetrical about the mean, slope downwards of both sides to infinity, and theoretically as an average, infinity edge. In the normal distribution, 99% of all measurements within the x plus 3s and x plus minus 3s. This is why limits on the control charts are called 3 sigma limits. So usually it is called as 3 sigma limits. So you can see here in the control chart, this is a basic typical control chart that we are describing here. That is the upper control, and there is an average center line X bar, the lower control limit like this. So whatever the process that comes under this it's under control. The data which is coming under out of that upper control and lower control is called that is the data is not the control. Okay, this is how we are going to draw the graph. So control chart analysis determines whether the inherent process variability and process average are at stable levels, whether one or both are out of statistical control, or whether appropriate action needs to be taken. Another purpose of using control chart is to distinguish between inherent and random variability of the process, variability attributed to the assignable cause. The sources of random variability, often referred to as common cause, these are the sources cannot be changed readily without significant restructuring of the process. Control chart types. There are two types of data, that is continuous and discrete, and there are two types of control chart: variable chart for use of continuous and attribute chart for the use of discrete data. So, like I said earlier, I'm going to just go through that type of chart. Variable chart means it is a powerful tool that we can use when measurements from the process are variable. So, the variable means the data can be continuously varying. Okay. So, example is the diameter of the bearing, electrical output of the fastener, something like that. So variable chart, expert R chart, expert X chart is also there. Attribute means P chart, NP chart, C and U chart. There are four types that we discussed in the earlier slides. Okay. See the attribute chart, although control charts are most often thought of in terms of variables, there are also version of attributes. Attribute data have only two values. It is confirming, non-confirming. That is pass and go. Sorry, pass and fail, go and not go, present or absent, something like that. Pass or fail. And whether the product is confirming to the specification or confirming to the specifications. Okay. Something like that. So, but they are still be counted, recorded, and analyzed. Some examples are presence of required label, installation of all required fasteners, presence of solder, continuity of the electrical circuit. Some other examples that we come across in the day-to-day manufacturing process. So we are also use attribute charts for characteristics that are measurable if the results are recorded in simple yes or no fashion, such as conformance of the shaft data when measured on a non-go, sorry, go, not go gauge or acceptability of the threshold margin to the visual or gauge check. So we're just not going to go and visually inspect that. We are going to inspect and we are going to say whether it's go or not go. From that, we are going to take some data and we are going to analyze it. So use of control chart. The power of control chart lies in their ability to determine if the cause of variation is a special cause. It can be affected at the process level or at the common cause that requires a change at the management level. The information from the control chart can be then used to direct the efforts of engineers, technicians, managers to achieve preventive and corrective action. The use of statistical quality control chart aimed at studying specific ongoing process in order to keep them in satisfactory control. By contrast, downstream inspection aims to identify defects. In other words, the control chart focuses on prevention of defects rather than detection and rejection. So it seems reasonable that it can be confirmed in practice that economy and efficiency are better served by prevention rather than detection. So the interpretation is like there are many possibilities for interpreting the various kinds of patterns. Control chart, if properly interpreted, the control chart can tell us much more about whether the process is in control and other out of control. So experience in training can help to extract clues regarding process behavior. Statistical guidance is invaluable, but intimate knowledge of the process being studied is vital in bringing about improvements. A control chart can tell us what to look for trouble, when to look, and cannot be itself tell us where to look and what cost will be found. Actually, in many cases, one of the greatest benefits from the control chart is that it tells when to leave the process alone. Okay, so these are some interpretation or advantage you can take. Significance of the control chart. So this is a typical control chart. The data you can see the plot it like this. Data we are plotting like this, and will have a benchmark of UCL and HCL in the bottom, and we can say whether the process is under control or not. Okay. So this is a typical run chart. Run chart means there will be a process average like this in the center line, and the data will be plotted like this. And we can see how much the individual data is varied from the average, we process average. Okay. For example, if you get a value like getting like this, okay, the product like so we can say this particular data it has more amount of variability from the process average, so that we can arrive using the run chart. Okay, when several successive points line up on one side of the central line, this pattern is called run. The number of points that in the run is called length of the run. Okay. So acceptance sampling, it is a statistical process of evaluating a portion of the lot for the purpose of accepting or rejecting the entire lot. It is an attempt to monitor quality of incoming product material after the completion of production. The alternatives to developing a sampling plan would be 100% inspection and 0% inspection. So the costs associated with 100% are prohibitive. The risk associated with 0% inspection are likely large. Therefore, some sort of compromise is needed. Okay. So sampling acceptance sampling means whether the total lot can be accepted or not. That we can able to check using this kind of method. Okay. Three commonly used sampling plans, that is single, double, and multiple. This is acceptance or rejection of the lot based on one sampling run. Double means results are not conclusive, then we can go for second sampling. Multiple sampling means requires sampling of several small lot. Regardless of what type of sampling plan is chosen, sampling errors can occur. A shipment of good quality items can be rejected if the large portion of defective items are selected at random. Likewise, a bad quality shipment can be accepted if the tested a small sample contains a disproportionately large number of quality items. So this kind of things will happen while doing the sampling plan. So there are two major risks associated with doing this kind of sampling plan, that is producer risk or consumer risk. So this producer risk is like, this is called alpha risk or type 1 error. This is a risk to the producer that good lot will be rejected. So that can also happen. That is only two possibility will happen. That is good lot might be accepted, sorry, will be rejected, or bad lot can be accepted. So that is called the consumer risk. Consumer risk means beta risk or type 2 error. This is a consumer risk of accepting a bad lot. Okay. When the bad lot is accepted, then it is called as consumer risk. Okay. When the lot is tested for quality, we can look at either attribute or variable quality data. Attribute quality data is either quantitative or qualitative data for which product or service is designed and built. Variable quality data or quantitative continuous measurement process to either accept or reject the lot. The exact measurements can be either destructive or non-destructive. Means that whether we can go for physical destructive testing procedure like core cutting or cube testing procedure, something like that. So just we can go through some typical example problems. So I'm going to explain that problem in step by step using some X bar R chart. Okay. So we all know X bar R chart comes under the variable control chart. So the question is given here. That is, they have given the range for 10 samples, and sample mean is given. X bar and R chart is given for sample size of size each 5. Calculate the values for central line and control limits for mean chart and range chart. Determine whether the process is under control. So that is the thing we are going to find, whether the process is under control. And next thing is we are going to find the control limits for mean chart and range chart. So step one will be the we are going to plot a table, and X bar and R chart is given here. That is given in the question. We're going to find the summation of X bar, which is the summation of all the values, okay, which is 106, and the summation of R, that is we are going to add all the samples range value, that is summation of R means 63. So the X bar will be the summation of X bar divided by the total number of samples, that is 10. So 106 divided by 10, 10.66. That is the X bar value, and R bar will be summation of R divided by number of samples, that is 63 divided by 10, which is 6.3. So they are given the A2, D4 and D3 value. So this is will be used for finding the upper control and lower control values. Okay. And this is the formula to find the upper control lower control limit. So X bar plus A2 plus R bar, and lower control means X bar minus A2 into R bar. Okay. So we are going to substitute all the values and we will find the values like upper control, lower control. And for R chart, the trial control limits for R chart, and the previous one is trial control limits for X bar chart. So we already find out the CL, that is center line. Upper control, lower control is given. We have found out, and the trial control for R chart means we know the. I mean, we have the formula, that is lower control formula is D3 into uh, D3 into R bar, and the upper control value is D4 into R bar. So D3 is 0, so the upper lower control will be 0, and in the D4 you can say that D4 value is given and the R bar is given, so we can multiply and find out this. So from this we can arrive the upper control, lower control and control limits, that is center line. So from this we can able to draw the graph. Okay. So the graph will be like this for X bar and R chart graph. So you can see here in the X bar there is a line in the top, that is upper control, which we have found out just now. Upper control 14.3 and the lower control is 7.0. So the center line, that is 10.664, is the average that we found in the beginning. Okay. And this is the point different data that we plot. For the given data we have plotted the, okay, the data for this. For similarly for a R bar we have plotted the range values here. Here the X bar values are plotted. Okay, we are going to check whether the process is in control or not. So from this graph, it is identified that all the values are coming under the upper control, lower control limit. So the entire process is under control. Okay. 5 samples are taken randomly. This is the next problem that we are going to solve. That is, they have taken the 5 samples, and for each sample, there is a 3 measurements per sample is taken. Okay, the readings are given here in the table. So you can say that there are sample number 1, 2, 3, 4, 5. For each sample, there is a reading like 1, 2, 3 reading. Okay, there are 3 readings for each sample. So in the previous problem, there will be having only 1 reading, but here there are 3 readings. In that case, what we are going to do? Okay. Similarly, we are going to calculate the control limits for X bar and R chart. So in the sample 1, the step 1 will be the calculation of X bar. That is, for sample 1, that is, we are going to add all the 3 readings and divide it by 3. We are going to take the average. That is the X1. So X1 will be 0.494. Similarly, for X2, we are going to add all the 3 readings divided by 3. So similarly, for all 5 samples, we are going to do that. And we are going to add all the 5 values, summation of all the values, and divide it by 5. That is the average. Okay, we will get X bar value. Okay, that is the X bar that we are going to take. That is center line. Okay, center line will be the X bar. Okay, and the R value is nothing but X max minus X minimum. That is the formula. It means that there are 3 readings. Out of all 3 readings, we will take maximum reading, that is X max, and the minimum reading, which is X minimum. We are going to take the difference between that. Okay, that will give the range value. That will give the range. So we are going to find R1. Similarly, for sample 2, 3, 4, 5. So once we find all the 5 samples range, we're going to find the R bar, that is the summation of R divided by 5. So you will get 0.018. So this is the R bar, that is center line for R chart. So from that we're going to can find the control limits value. So this is the typical problems that we can come across for statistical control chart type of method. So this is the reference I've taken for preparing this lecture. Thank you.